Today's lesson is over section 4.6, where we'll be modeling with exponential and logarithmic functions. Okay, before we start, I would like to show you the list. So here's the list of all the general formulas for modeling that we may or may not use, just so you have them at your disposal so you can go ahead and write them down. I'll briefly go through them with you. N sub t equals n sub 0 times 2 to t over a power is doubling time. So it's exponential growth, but it's doubling. And you can change that. You can, if it says it triples, you can change the 2 to a 3, or quadruples. For a certain amount of time, you can change the 2 to a 4, depending on the situation. So it works for a lot of different things. N sub t equals n sub 0 times e to the rt. This is just exponential growth with a relative growth rate, which is the r value. M of t equals m sub 0 times 2 to the negative t over h power. This is half-life. Okay, also for doubling time and half-life, that value is telling you how fast it's doing it. So a is how fast it doubles, so the amount of time it takes to double. H is the amount of time it takes to be half of what it was. And then the next one, m of t equals m sub 0 times e to the negative rt power, which is very similar to exponential growth. It's called radioactive decay. Next one is Newton's law of cooling, which is T of t is equal to T sub s plus T sub 0 times e to the negative k t power. pH scale is given here, so it's negative law, and the H plus is the concentration of hydrogen ions. Okay. M is this next one is the Richter scale. Okay, where log of I, which is the intensity of your earthquake that you're talking about, is divided by the initial intensity of just a standard earthquake, which is 10 to the negative fourth. And this last one is the decibel scale. Okay, where it's 10 times log of I, so the intensity of your sound, divided by the initial intensity, which is a barely audible sound, which is 10 to the negative 12 power. Okay, so those are some just general equations that we can use. And so depending on the situation, we need to pick the correct one that fits what we're talking about. So example 1 says a population of 1,000 bacteria doubles every 3 hours. So here they want us to first write the equation of the population at time t. Okay, so going back, I see the word that says doubles, and so then that means it must be doubling time. Okay, so I want n sub t equals n sub 0 times 2 to the t over a power. Okay, so I'm going to insert my stuff in. N sub 0 is my initial amount. So it's usually what anything with sub-zero means. It's an initial amount that you're starting with. They give you 1,000 bacteria. Sorry about that. And so now times 2. And so now we need to describe what the a value is, but they give it to you. So it would be t, because we don't know how much time has gone away, over 3. So that would be my answer. Okay? Then they want to be able to find what is the population after 8 hours. So using our formula, t is 8, so then 1,000 times 2 to the 8/3 power. Okay, so here probably need a calculator. So if I plug that in, that gives me 6,349.6. Okay, So here we can just round up, or just leave it that way. Okay, so that would be my answer. Okay, next one is, when will the population first exceed 200,000? Okay, so here there's a little bit more math involved. So your final amount is that n sub t, or n of t, but we don't know what t is. Okay, so now we need to be able to solve for t. So I want to move the 1,000 over. That gives me 200. Okay, now I need to be able to take the log of both sides. I'm actually going to use the ln. Doesn't matter which one you use. Now I can use my power property and move it down. Okay, and I can divide this ln of 2 away. And then I can also multiply both sides by 3. So now 3 times ln of 200 divided by ln of 2, it's going to be 22.93, and then that would be in years, or sorry, hours, because that's what we were talking about earlier. Okay, so that would be my answer. Okay. Next one, example 2, has us population with a relative growth rate of 2.25% per hour. Starts at 8,000. Okay, so it says relative growth rate, so that must mean we need to use the equation with a relative growth rate. So n sub 0 times e to the rt power. They already give us our rate. So n of t equals, in our starting position, starting amount is 8,000 times e to the, now since it says 2.25%, I need to do 2.0225 times t power, and then that would be my equation. Okay, so now I need to be able to find the population after 9 hours. So let's plug in 9. So plugging that into my calculator. Gives me 9,795.68. Okay. And here we can also round up to give me 9,796. Okay. So then the next position, or next problem or part, is when will the population first exceed 500,000? So we're kind of doing the same thing that we did in the last C.